Hi, and welcome to the 9th episode of the Sienna training series. I'm Kate Doubleday, and today I'll be talking about how to set up and run a single operations problem in Sienna Ops. So Sienna is an open source platform for power system modeling, simulation, and optimization with 3 core applications. Sienna Data focuses on efficient data input, analysis, and transformation. Sienna Ops, which is our focus today, enables system scheduling simulations by formulating and solving optimization problems like unit commitment, dispatch, and optimal power flow. And Sienna Dyne enables system transient analysis, including small signal stability and full system dynamic simulations. Each of these 3 applications is written in a combination of packages in the Julia programming language. So today our focus is on Sienna Ops, and in particular, we'll be focusing on using Power Simulations, which is the foundational package for Sienna Ops, to formulate and solve an operations problem. In a previous video about how Sienna Ops works, we introduced some key concepts, including formulations, templates, and decision models. The idea is that in Sienna Ops, we define templates for behavior that include the descriptions or the formulations for how each component in the system should behave. We used an analogy of making a robot, which is our data set, do different behaviors. So that included, for example, making a walking template where we tell every arm in the system or in the robot to pump and every leg to stride. We can apply the same template to different robots and get different movements and different behavior. We can also similarly apply different templates to the same robot or the same power system. So we could change from walking to dancing with the power system. We could change from an economic dispatch to a unit commitment or vice versa. A template is just this recipe for behavior. It has no data attached. When we combine a template with a power system data set, we get a decision model. So that is the full set of both data and equations that can define an optimization problem. So when we switch from robots to power systems, today we're focusing on developing a unit commitment operations problem. So when we talk about doing a unit commitment and economic dispatch simulation, typically when we think about a day ahead unit commitment, we're talking about something like a 48-hour optimization horizon that includes both the 24 hours, the next 24 hours where we're interested in solving the least cost operations for the system, as well as a 24-hour look ahead to make sure that our behavior at the end of the day goes smoothly into the next day. This is one window. And by moving that window forward in 24-hour increments, we can solve one unit commitment problem after another and eventually get to a full time series simulation of those decisions over the course of a week, a year, whatever the full time horizon is. We could also take a sequential approach of feeding each decision made in a unit commitment window into an economic dispatch that represents what actually happens during that day of operations once we move from day ahead forecasts, which might be off, to a true up of what is actually happening with real-time data during the economic dispatch. So in today's video, we're focusing on just the first piece of the puzzle, one operations problem, which is the building block to eventually get to a sequential simulation. This represents one optimization problem run through a solver. Checking one operations problem like this to make sure that it solves successfully is a great first step in debugging to make sure that your data and your equations are correct before you get into the complexity of running a long-term sequential simulation. So in the next video, we'll take it to that next stage of running a series of operations problem in a full simulation, which is a sequence of these decision problems. For now, however, we're just going to focus on that first piece. So I'm going to start this example by loading in a couple of the power of the Sienna data packages and a couple of the Sienna ops packages. So power systems and power system case builder, which are part of Sienna data, and power simulations, as well as an additional extension package, hydropower simulations, which are part of Sienna ops. I also am loading in Highs, which is an open source solver. You could use the other proprietary versions as well, like Gurobi or Express. So once we have those loaded in, and again, this is assuming that you already have them installed. So there are some installation instructions on the Sienna website if you first need to install the packages. I want to share what versions we're using in this demonstration because Sienna is under active development. And so changes are expected to the syntax in these packages. And so if you're getting any errors in trying to replicate what I'm doing here, the first thing I would do is verify what packages, what versions you currently have loaded in compared to what we have here, and check the documentation for those packages for if there were any syntax updates. Finally, the last thing I'm going to do is I'm going to define a solver for using this optimizer with attributes function, which is part of Sienna, to load in our highs optimizer. In this case, we're going to use a pre-existing system, which is accessible through Power System CaseBuilder.jl, which is one of our utility packages for saving and loading existing systems. I will say that the first time you do some of these functions, like the package load in or building a system with Power System Case Builder, you might find that it takes quite a lot of time in comparison to what you see here, because it will need to download either the data sets or the packages. All right, so I've defined a system, and it includes a variety of components already defined, as well as the time series that we can use within our operations problem or sequential simulation. So I want to note here that this is just data. We have no description yet for how this is going to behave, but when we make our template, we need to make sure that we define the formulations for how each of these types of static components that have different behavior options, how they're going to behave. So that includes our injection devices like renewable and hydro generators and loads, as well as how our branches are going to behave. That includes lines and transformers. And we also have some services defined, these reserve services. In particular, we're also interested in making sure that we define our thermal generators with the on-off decision binary variables that define a unit commitment problem. So now let's start that process by defining a template, which we're going to populate with those formulations. This is a pretty empty template, and you can see that so far all it's defined is a default copper plate network model, but we don't have any formulations for devices in this template yet. So let's start adding formulations to this template, starting with the thermal standard components, which will give what's called a thermal standard unit commitment formulation. So each type defined by powersystems.jl can be given different formulations that are available in powersimulations.jl. And you can find those options in the powersimulations.jl formulation library, and I'll link that in the video description. So by the name, you can tell this is a unit commitment formulation, and this includes those on-off decision variables. And I've added this to our template. So if we print the template again, we can see that we're starting to populate. I'm sorry, I have to actually run that command. Once we set the device model and print the template, you'll see that we're starting to populate the formulations matched to each device type. So we'll need to do that for all injection devices, branches, and services in the system. Part of making sure that you've set up a template correctly is to look at the system that you are modeling, the data set, and make sure you've defined something for every type, every static component type that should have a behavior attached. Not all of them do. Some of them are arcs, for example, are just sort of topological components, but this is a good place to check your list here and make sure that you've defined a formulation for everything that needs one. So I'm going to go ahead and do that in batch for everything that's not the thermal standard devices. That includes device models for all of my injection devices, device models for all of my branches, and service models for the reserves. And I can print that template one more time and see now, okay, I've got a full recipe here. I've got a full template for behavior for every component type in the system. This on its own is just, again, this description of behavior. We don't have any data attached to it yet. And so now we're in that stage where we're going to define a decision model that takes both the template for behavior and our data set, the system, and defines a complete optimization problem. Here we're just looking at that first building block again. So the first 24-hour horizon using the time series that's already available in the data set. That's going to print out a summary that's pretty similar to what we saw before in terms of defining what formulations are being attached to different types. And we can now build and solve this problem. Notice that in this build definition, or call to the build function, I'm also defining an output directory. And while this is working, which might take a moment, I'm going to go ahead and pull up that directory, which is where I'm running this tutorial. And we can see that as it builds the problem, and then in a moment when we run the problem, it's going to start populating this directory with the records of the simulation. And so if at any point we need to load the data back in, check anything that we either input or output from the simulation, it will be in this directory. So the build step is complete, and we see that that built successfully. And so now I'm going to solve that problem. So as this is solving, we can similarly see that more files are going to start populating this directory. And a couple of them that are useful to note is that you'll see it just populated a record of the system, including the system JSON, time series, and metadata files. So if we ever want to double check what we ran in the simulation, we can just directly load the input data set back in. It also exported a log. And so this log file includes a variety of update statements as it's running through, but also the time and memory allocations for various steps in defining the operations problem and solving it. And so if you're having various debugging questions, this might be a place to check for those output statements and allocations. And then finally, you'll also see that there's this problem results.bin file that records the outputs of our simulation. And those will be available for us to read back in the future once we close out this current Julia instance. So for now, I'm going to go ahead and load the optimization problem results back in. And we can see that this gives me a very handy list as well of the various expressions, parameters, and variables that are available in the results for me to load back in as data frames to inspect or post-process as I'd like. So that includes our decision variables, and importantly, for this unit commitment problem, one of the ones we were interested in, of course, is the on-off decisions for the thermal standard generators. So we can go ahead and use some of the available functions to read in important metrics from our results, from our simulation results. That could include, for example, the objective function, as well as the the data from any of those variables, parameters, or expressions. So I can read back in the on-off decisions for the thermal generators as a data frame for me to check post-process as I'd like. So I'm going to stop this video here, but we are going to follow this up with another video on running a sequential simulation that stacks these building blocks together over time, and also a follow-up video on additional results processing with Power Analytics and Power Graphics that can take what I'm showing here in terms of reading the results back in a few steps farther to help in the post-processing. So thanks very much, and we'll see you in the next video.